Okay, this is our PowerPoint. It says Introduction to Structural Member Properties, but this is about moments of inertia and beam deflection. Structural member properties. Structural members, we're talking about things that give any kind of structure, buildings, cars, wings of airplanes, the things that make it the shape it is. And an important principle of that is the moment of inertia, which is represented by the letter I, and it has to do with the cross-sectional shape of that item. So it's measured in inches to the fourth power. You should take notes in your notebook as you go through this PowerPoint. If you need to pause it to take the notes down, you should totally do that. And what this tells us is how stiff is the object. In other words, how easy is it to bend, or how hard is it to bend the shape. So for instance, we have these happen to be 2x6s, which are actually a 2x6 piece of wood is actually 1.5 by 5.5 inches. And one is laid down flat like this, and one is stood up like this, which is actually the way they're used in buildings, standing up like this. And you're going to see why. These are the same material, the same length, and they're the same shape, they've just been switched. And what makes them different? Which one is easier to bend? Well, if you've ever actually had a 2x4 or 2x6 laying around and it's been propped up on one end and you've stepped on it, you're going to have an idea which one is easier to bend, even before we do the calculations. And the truth is, this one that's flat is easier to bend down. It's going to bend a lot more. This one's going to bend a little bit, but not anywhere near as much as this one will. So when we calculate the moment of inertia of rectangles, this is the formula we're going to use. This is in the back of your book in your formula chart, in the back of your engineering notebook. So copy this down onto the notes page I handed you. And notice that the base and the height is going to depend on which direction I have this sitting. Because the height is cubed, you do have to be sure to put the base is the horizontal one and the H is the vertical one. And you have to put those in the right place or you will not get the right answer. So if we're talking about beam A, and you should write these down in your notes, I gave you the table that goes with beam A. Here are the dimensions. This is your base and this is your height. Plug them in here and use your calculator and get your answer. Notice that inches times inches cubed gives us the inches to the fourth. Pause this if you need to write it down. This is beam B. We've now set it down. So this is now the base and this is now the height. Plug them in and there's your answer. Pause it if you need to copy this down. So what we see is for beam A, the one standing up, its moment of inertia is 21, while the flat one is 1.5. That means this one is 14 times stiffer. Stiffer or harder to bend. The way we calculated this 14 is we did 21 divide by 1.5. You're going to have to do this on the knowledge check, so make a note of how we came up with which one is stiffer and how to calculate this number. Remember, you got this number by doing 21 divided by the stiffer one divided by the weaker one. We use different shapes of beams when we're building. We could use something like a 2x4, but when we talk about metal pieces, we use different shapes like an L beam, an I beam, a C channel. And we use these different beams because when they have the same area, the same cross-sectional area, they have the same weight. But they'll have different moments of inertia. Which is better, a bigger moment of inertia or a smaller moment of inertia? Well, the bigger moment of inertia has less bending. So these two have the same area, so the same weight, the same amount of materials being used for them, so probably the same cost for these two. But this one has a much higher moment of inertia. That means this one is going to be much stiffer. In fact, 10 times stiffer than that one. This one has the same dimensions, but this one uses way more area. So way more material, it's going to be a lot heavier. and its moment of inertia only went up slightly from here. That's why we use these shapes like an I-beam. Modulus of elasticity is the ratio of stress to strain. We're going to talk about more of how to find this when we do stress and strain in a few days. But for now, this is usually an item that we're given for a certain material, like we know the properties of, say, steel. Or if we were coming up with a new material, we would have to calculate this, and I'll show you how we calculate it in a few days when we do stress and strain. In general, a higher modulus of elasticity produces a greater resistance to deformation. So now I have two planks, two pieces. The first one, A, is made out of wood, Douglas fir, and the other one is out of plastic. And notice they're the same length, the same exact dimension, so they have the same area, and so they have the same modulus of the, the same moment of inertia, because the end shape is the same. So what's going to make these different in how much they bend? Well, the plastic one will bend a whole lot more than the wood one, and that has to do with the modulus of elasticity. And how much it bends is going to tell us our deflection. This is a delta, which means the change in. So when we have delta max, we're talking about the maximum deflection, the maximum deformation, how much it'll bend in the middle. So here's our formula for this. Again, this is already on your formula chart. Notice that L is the whole length of the beam. E is the modulus of elasticity, which you're going to have to be given for a type of material. F is the force we're applying in the middle. And I is the moment of inertia, which we just learned how to calculate a moment of inertia. So I also gave you this table so you can do these calculations along with this PowerPoint. Do be sure when you put this into your calculator that this bottom part is going to have to be in parentheses. So we're going to do it for A. Here's our same information. Plug in F, plug in L. Be sure you only cube L. Don't multiply, then cube. You have to cube, then multiply. And on the bottom, if you put this in your calculator, you need to put the whole bottom in parentheses or you'll get the wrong answer. Be sure you can plug it in and get the same answer they do. So what it's saying is that for this beam, if I put 250 pounds on there, it's going to change 0.1 inches. Not bending very much. 0.1 inches, very small. For the plastic one, same calculations. Plug everything in, calculate it on your calculator, and you get a 1/2 inch. That's a lot more change than just 0.1. So this one is going to have a lot more bend right here, and that's what we're measuring. That'll be a 1/2 inch. This will be 0.1 inches. That's it for the beam deflections.